So, hello everyone and welcome to our Module 3 Part 2. And for today's topic, we are going to talk about reliability. So, this is one of the facets or characteristics of what makes a test good. And in this session, I'm really going to be technical here, but I will try to simplify it for you. So, I recommend that you read ahead with this topic, especially reliability and validity, and go back to this lecture for you to have a supplement and extra information about it. Okay, to clarify some misconceptions and also clarify some concepts that you don't understand. So that's what I recommend, because in this session, this is very technical. At the same time, with validity, I'm going to be very technical, but I will try to simplify it for you. So without further ado, let's go and take a deep dive on the world of reliability. Okay, so what is the concept of reliability? A reliability coefficient is an index of reliability, a proportion that indicates the ratio between the true score variance on a test and the total variance. Okay, so if you recall our previous session in norms, we talked about the classical test theory. So in classical test theory, I talk about that the score on an ability is presumed to reflect not only the test taker's true score on the ability, but also the error. So in classical test theory, so your score in a test is presumed to be your true score plus error. So when we say error, these are variations or variables that is not related to what we are measuring. So error refers to the component of the observed test score that does not have anything to do with the test taker's ability. So if we use X to represent the observed score and T to represent the true score and E to represent error, so we can have a formula that is X is equal to T plus E, or your observed scores is equal to the true score plus error. So that's in essence the classical test theory. A statistic used in describing sources of test error is, of course, variability. If you remember, in standard deviations, we are looking for how spread out the data is, how varied the test scores are. So, in the statistic we use in describing the sources of error or sources of test score rather is the variance, okay? Or the standard deviation squared. So variance from true differences is true variance, and variance from irrelevant random sources is error variance. Thus, this formula, which is sigma squared is equal to sigma squared TR, which is the true variance, plus sigma squared error. So it's kind of the same with the classical test theory formula, but we usually use the statistic, which is the variance. So therefore, the term reliability refers to the proportion of the total variance attributed to true variance. And here is a rule of thumb that you need to remember. The greater the proportion of the total variance attributed to true variance, the more reliable the test is. So again, so the greater the proportion of the total variance attributed to true variance, the more reliable the test is. So it just simply means that if your reliability coefficients, if we got a reliability that is greater, okay, than that of the error, then we can say that the test is reliable. Okay? So, like I said, error means it's not a mistake. So, it's not a mistake, but error when it comes to measurements, when it comes to psychological assessment, it simply means that this is inaccuracy in our measurements. It means that these are extraneous variables that may have affected the score of our participants or our test takers. What are the different sources of error? So firstly, of course, the first error that we usually see is in test construction. So especially in item sampling or content sampling. Item sampling or content sampling. Variations among test items within a test as well as variations among items between tests. So for example, it is the differences in which the items are worded and the exact content sampled. So for example, in your midterm exam, okay? So in content sampling, okay, how much of the modules 1 to 3 have I included in the test? Is it well sampled? It means that does all modules have the same number of items? Or in item sampling, how did I word the exam? How did I write it? It is also a source of error. So from the perspective of the test creator, a challenge in test development is to maximize the proportion of the total variance, that is the true variance, and to minimize the proportion of the total variance, that is error variance. So another source of error is, of course, test administration. So sources of error variance that occur during test administration may influence the test taker's attention or motivation. So in particular, the test taker's reactions to those influences are source of one kind of error variance. So examples of error variance when it comes to test administration is of course the environment. So does the temperature of the room well ventilated? The level of lighting? Can the test taker see what he is answering? Test taker variables are also a source of error. So, for example, does the participant feel anxious or depressed that day, or is there any problems prior to the administration of the test, or physical discomfort? Maybe the test taker is sick. So, examiner-related variables. So, physical appearance of the test administrator is also a factor. The demeanor. So, and also the presence and absence of the examiner. So, during face-to-face classes, right? So, there is always a presence of a proctor. So, the presence and absence of a proctor can actually affect your test scores. So, especially if the proctor is whether friendly or very strict. So, it affects your performance in answering a test. So, test scoring and interpretation. So, in projective tests, so of course, the source of error there is the subjectivity of the scorer. So, the scoring depends on the examiner or the test user. And also, for example, in computer-assisted testing, of course, there is technical glitches. Okay, so also, this is also relevant, right, in your Canvas. Sometimes Canvas marks your answer wrong, even though in my answer key, it is correct. So other sources of error. So this is based on research. So for example, social desirability. So females, for example, may underreport abuse because of fear, shame, or social desirability factors, and over-report abuse if they are seeking help. Okay? So on the other hand, males may underreport abuse because of embarrassment and social desirability factors, and over-report abuse if they attempt to justify the report. Okay, so those are some sources of error. So, when we say again reliability, it means relatively free of measurement error. So, it means that the true score must be higher than the error variance. So, consistency in the type of test result a test yields, and measure of consistency of results from one administration to the next. So if, for example, you are going to administer a personality test to a test taker in year 1, then after year 2, after you re-administer the same test again, it must have almost the same results. Okay? Or it must yield almost the same results. Generalizability consistency. So these are interwoven concepts. if a test item is reliable, it can be correlated with other items to collectively measure a construct or content mastery. So it just simply means that if the test item is reliable, it means that we can somehow relate it or generalize it to other measures with the same construct. Or for example, in your test, we can say that if the test items in your midterm exam is reliable, it can generalize that, okay, we can really measure your mastery when it comes to psychological assessment topic. So there are different kinds of reliability, but of course, I'm going to simplify it and at least give examples on where we can use these kinds of reliability. But in your laboratory session, I will discuss even deeper item consistency. Okay, so and what statistical use we use when it comes to solving the item consistency. But the kinds of reliability here are the test-retest method or time sampling, parallel forms method or item sampling, and split half method, and of course the item consistency method. So test-retest method, time sampling. So it evaluates the error associated with administering a test at two different times. So again, okay? So it evaluates the error associated with administering a test at two different times. So it is applicable when the tests being measured do not change over time or it is stable. Time sampling method or test-retest method is only applicable for traits when we are measuring traits such as intelligence, personality, because it is relatively stable. So test-retest reliability is an estimate of reliability obtained by correlating pairs of scores from the same people on two different administrations of the same test. And it is called coefficient of stability. It means this is the estimate of test-retest reliability obtained during the time interval of 6 months or longer. So the passage of time can be a source of error variance. The longer the time passes, the greater the likelihood that the reliability coefficient will be lower. So how do we measure the test-retest method or the time sampling? In time sampling method, we administer the same test on two well-specified occasions and then find the correlation between the scores from two administrations. So as you can see here, the statistical tool that we use when measuring time sampling method is of course correlation. So either Pearson's R, we administer the same test in two different time periods. So that's test-retest method. So this is an illustration. So like I said, the same test in time 1. So usually the best interval of time is 6 months, especially for traits. And then we administer again the same test on a different time. So, and then we calculate the correlation between the two tests results. So that's test-retest or time sampling. So, but there are, of course, problems when it comes to test-retest method. Firstly, the carryover effects. It occurs when the first testing session influences the scores from the second session. So, usually, the test-retest correlation usually overestimates true reliability. So, when we say overestimate, it means that the reliability score is more than the true or actual reliability of the test. So, carryover effects usually happens when, for example, I administer to you your midterm exam and you didn't pass the midterm exam. So, the next year, you took again the same midterm exam. But of course, somehow, you already studied the material, so you carried over what you have learned from the previous one to the next administration of the test. So that is also practice effects. Carryover effects and practice effects are almost similar. So it is one type of carryover effect. So this is where some skills improve with practice. And usually the second administrations are usually higher than the first. So like for example, in pre-test, post-test, for example, if I administered a statistics diagnostic test in the first part of our class, and then now there is an intervention. So which means that you have review classes of the statistics, right? So now that you have reviewed statistics, the next administration, you already know what are the concepts in statistics. Therefore, your second test score is much higher than your first test score. So, again, in time sampling method, so we must consider, of course, the time interval. So, it must not be too close. The administration of the test must not be too close or too far, or else the correlation coefficient will become lower. So, of course, consider the events in between or the intervention that happened time in between administration. So we also have another sampling method, which is parallel forms. So this is item sampling. So it compares two equivalent forms of a test that measures the same attributes. Two forms use different tests. However, the rules used to select items of a particular difficulty level are the same. Coefficient of equivalence, an estimate of parallel forms reliability or alternate forms reliability. So in parallel forms, so we have two different tests, okay, with the same content, with the same difficulty, and then we try to evaluate how equivalent they are. So, for example, two similar math tests. So, for example, I want to measure your mastery when it comes to multiplication. So, I have two different tests when it comes to the test items, but they have the same content, which is all about multiplication and same difficulty. So it's like form 1 and form 2. And then I'm going to administer it at the same time. And I will try to estimate how parallel or how correlated your scores are. So parallel forms of a test exist when for each form of the test, the means and the variances of observed test scores are equal. In theory, the means of scores obtained on a parallel form correlate equally with the true score. More practically, scores obtained on the parallel test correlate equally with other measures. So, in parallel forms, it simply means that if your scores in two parallel exams are correlated, then it means that it is also correlated with your true score or your true performance of that test. So, alternate forms are simply different versions of the test that have been constructed so as to be parallel. Although they do not meet the requirements for legitimate designation, parallel, alternate forms of a test typically designed to be equivalent with respect to variables such as content and level of difficulty. So, in some tests, for example, like intelligence test, they have different forms. So, culture fair test has 4 forms. Okay. And they have form A, form B, form C, form D. And this is given to a particular demographic. So, for them to measure the correlation between the different forms of tests, so they give the 4 forms of tests at the same time. And then, from the test scores of that 4 forms, they would try to get the correlation coefficient to those 4 scores from the 4 forms of the test. So once they have established the correlation coefficient of it, and if it is high enough, so it means that, for example, if I give form A to one test taker, it would also yield a reliable or almost the same result as if I give the test taker form B or form C or form D. So, obtaining estimates of alternate forms reliability and parallel forms reliability is similar in 2 ways of obtaining estimate of test-retest reliability. So, in here, 2 administrations with the same group are required, and the test scores may be affected by factors such as motivation, fatigue, or intervening events. such as practice learning or therapy, although it is not as much as when the same test is administered twice. So, the only disadvantage when measuring item sampling or parallel forms method is that there are extraneous factors such as motivation and fatigue, especially if the forms of the test are long. Okay, so it may affect the test taker's performance and also practice and learning. So if you give similar forms of a math test, so the test taker might already know how to answer form B. So the source of error that we are looking for in parallel forms is of course the item sampling. So this is the inherent computation of alternate or parallel forms reliability coefficient. So test taker may do better or worse on a specific form of test, not as a function of their true ability, but simply because particular items that were selected for the inclusion of the test. So, for example, one test taker may perform better in Form A than in Form B because of the content sampling of the items. So, I might, for example, in set A that I give to one student, the one student perform better than when I give him set B. It's because maybe the items that I have sampled in set A are items that he have studied, than in Form B, the items that I sampled wherein he did not review for it. So again, this is an visual illustration of what parallel forms reliability is. Form A, Form B, okay, is administered at the same time, and then their correlation is then measured. So item sampling can be administered to the same group of people at the same day. Two test forms of the test are given at different times. It minimizes the effect of memory for the content of previously administered form of the test. And of course, the sources of variation or sources of error that we are looking for are random errors and differences between the forms of the test. The problems for parallel forms, it is first difficult to develop two forms of the same test. Okay, and of course, it is the practical constraint. So, making it requires a lot of time and resources. So, the statistics that we use is, of course, person product moment correlations, or persons R. Okay, so the ratio is used to determine the degree of variations in one variable that can be estimated from the knowledge about variation in other variables. So next is the internal consistency estimate of reliability, or the estimate of inter-item consistency. How homogeneous or heterogeneous are the items in a certain test. So what we are using here are the split half, KR20, and Cronbach alpha. So first method of measuring internal consistency is split half. So inter-item consistency, this is the degree of correlation among all items on a scale. An estimate of split half reliability is obtained by correlating two pairs of scores obtained from equivalent halves of a single test administered. So we are measuring whether the traits or the items are homogeneous. It means that the items measure single trait, or heterogeneous. The item measures different traits. So example of a homogeneous test is, for example, a math test that measures your ability in multiplication. So the items must only contain a single trait, which is items that are about multiplication. For a heterogeneous items, my example would be a diagnostic math test wherein you are being measured your math skills such as addition, subtraction, multiplication, and division. So there are 4 different domains or 4 different traits that are being measured. So a test is given and divided into halves that are scored separately. The result of one half of the test are compared with the results of others. Options are, if the test is long, the best method is to divide the items randomly into 2 halves. But if the test is, as they go along, it become more progressively difficult, so they will use the odd-even system. So those are the ways in which you can measure split half. reliability. So the computation of a coefficient of a split half reliability generally entails 3 steps. Step 1, divide the test into equivalent halves. Step 2, calculate a person's R between two scores of the halves of the test and adjust the half-test reliability using the Spearman-Brown formula. So if you're going to do a split half method when it comes to reliability, so first you divide the test into halves. If the test is long, you can equally split it in half. But if it's like a power test wherein that items become more progressively difficult over time, so you need to divide it using the odd-even system. And then once you get the scores of the two halves of the test, you correlate them using Pearson's R and use Spearman-Brown formula as a correction to the R. For the Spearman-Brown formula, so this is an estimate of reliability based on two halves of the test that would be deleted. So this is a correction for half length and allows estimation of the correlation between the two halves if each half had been the length of the whole test. This is used if the two halves have equal variances. So this is, for example, you have 100 item test and so there are equal number of items for each half, like 50-50. So this is the formula. So don't worry, we will not manually compute the formula for Spearman-Brown, but everything will be done via SPSS. So don't worry, everything that I'm talking about, especially in reliability, can be done in SPSS. But just take note of the formula for you to understand how it works. So RSB, or R persons are corrected, that is from the Spearman-Brown formula, is equal to, sorry for the error, is equal to 2RHH over 1 plus RHH. So wherein RHH means the person's R score of the two half of the test. So next is Cronbach alpha coefficient, or Cronbach coefficient alpha. So this is used if two halves of the test have unequal variances. For example, you have 110 items. So there are unequal variances. Or for example, you have 107 items. So there are unequal variances. So you cannot split them directly into half. And it provides the lowest estimate of reliability that one can expect. It can also confirm that the test has a substantial reliability. So if the alpha is high, so meaning the reliability of the test is acceptable. But if it is low, it means that the test is not reliable and gives less information. So another method of estimating internal consistency is the Kuder-Richardson, or KR20. So this is by G. Frederick Kuder and M.W. Richardson. This is evaluating reliability within a single test administration, and it is often used for dichotomous items. So when we say dichotomous items, these are items that have questions that are about yes or no, or true or false. And this is also used for items that have correct answer. So it finds the proportion of people who got each item correct. This is the formula for KR20. So KR20 is equals to K over K minus 1 times sigma PQ over sigma squared, or the summation of PQ over sigma squared. So KR20 is the reliability estimate, N or K is the number of test items, sigma squared is the variance of the total test score, P is the proportion of people getting the item correct or they pass the item, Q is the proportion of people getting each item incorrect or fail, and summation of PQ is the sum of the products of P times Q for each item of the test. So Cronbach, or coefficient alpha, so I think I have also mentioned this a while ago, but Cronbach coefficient alpha, this is often used for personality and attitude scales. This is for items that have no right or wrong answers. So this is also used for Likert scales. So responses which indicate where one stands on the continuum between agreement and disagreement. So usually this is the most commonly used estimate when it comes to internal consistency. So the coefficient alpha is the preferred statistic for obtaining an estimate of internal consistency reliability. Coefficient alpha is widely used as a measure of reliability, in part because it requires only one administration of the test. So coefficient alpha typically ranges from 0 to 1. So this is the formula for coefficient alpha. So just remember the formula again, familiarize it. So coefficient alpha is equals to k over k minus 1 times 1 minus sigma squared minus summation of sigma squared 1 squared over sigma squared. K is equals to the number of items. 0 sigma 1 squared is the variance of individual test items, and summation of sigma 1 squared, sum of the individual variances, and sigma squared is the variance of the total test score. So again, just familiarize with the formula, and all of this formula can be done in the SPSS. So don't worry about the calculations. So let's review. What are the different methods of reliability estimate? So this varies first in the source of our errors. So the first one is for time sampling. So example, same test is given into two different points in time. So the method of estimating the reliability is using the Test-Retest method. So how it is assessed? So you get the correlation between the two scores of obtained in two different occasions. So next, if the source of error we are looking for, the source of error that we are looking for is the item sampling. So this is where different items use to assess the same attribute. So that method is either alternate forms or parallel forms. So how do we get them? Get it? So you get the correlation between equivalent forms of the different tests that have different items. Okay? Next is internal consistency. So you're looking into how homogeneous or heterogeneous an item in the test is. So there are three ways to assess it. So split half, KR20, and coefficient alpha. So in the first one, in the split half, you get the correlation and then you correct the correlation between two halves using Spearman-Brown formula. The second one is used, the Kuder-Richardson 20 is used if you have dichotomous items and there are right or wrong answers. And the third one, which is the Cronbach alpha, this is used when there is no wrong or right answers or items. And this is used when you want to know how homogeneous or heterogeneous your test items are. So another kind of reliability is what we call the inter-rater reliability. So what we get here is the coefficient of inter-scorer reliability. This is determining the consistency among scorers in the scoring of a test. This is assessed by having two or more independent judges score the test, and then the scores are then compared to determine the consistency of the rater's estimate. So inter-rater reliability is often used for projective tests, especially since projective tests are subjective. It depends on the rater's scoring. So they need to know how reliable the rater's scorings are. So they use the coefficient of interscorer reliability. So one way to test inter-rater reliability is to have each rater assign each item on a test score. And this is also known as the percentage agreement method or percent agreement method. So for example, each rater might score items on a scale from 1 to 10. Next, you would calculate the correlation between the two ratings to determine the level of inter-rater reliability. Raters then determine which category each observation falls into and then calculate the percentage of agreement between raters. So if the raters agree 8 out of 10 times, the test has an 80% inter-rater reliability rate. So for example, if two raters assign the same ratings to 40 of 50 behavioral observation, the percent agreement is 80%. So percent agreement is easy to calculate and interpret, but it can lead to erroneous conclusion because it does not take into account the level of agreement that would have occurred by chance alone. This particular problem for behavioral observation scales that requires raters to record the frequency of a specific behavior. In this situation, the degree of chance agreement is high whenever the behavior has a high rate of occurrence, and percent agreement will provide an inflated estimate of the measure of reliability. So, another method in which we can use inter-rater reliability is coefficient in with regards to correlation coefficient. So, there are two, the kappa statistic and the coefficient of concordance. So, kappa statistic is also known as kappa coefficient or Cohen's kappa, and it is used when scores or ratings represent nominal or ordinal scale of measurement. So, if your behavioral observation checklist is using nominal or ordinal scales, so you will use kappa statistic to measure the reliability of it. So, coefficient concordance is also known as Kendall's coefficient of concordance, and it is used to assess inter-rater reliability when there are 3 or more raters and ratings are reported as ranks. Okay, so it is also used when your behavioral observation checklist or projective test uses ranking or ordinal scale as a form of measurement. So how now do we try to evaluate reliability and the individual scores of each test taker? So we go into the concept of standard error of measurement. So reliability coefficient is useful for estimating the proportion of true score variability in a set of test scores, but it is not particularly helpful for interpreting an individual's examinee's obtained test score. So, the reliability coefficient is useful if we have a lot of participants or test takers whom we can get the data from. Okay? So, it's useful for us to determine how reliable the measurement is, those methods of reliability coefficient that I mentioned. But we do not know, for example, or we cannot rely on the traditional reliability coefficient methods if we want to know or interpret if we want to really evaluate the test taker's true score. So, for example, when an examinee receives a score of 80 over 100 item test that has a reliability coefficient of 0.84, for instance, we can only conclude that since the test is not perfectly reliable, the examinee's obtained score might or might not be her true score. So the score of 80 here might or might not be her true performance score. So it might be because there is error in it. So if you remember, go back to classical test theory. The standard error of measurement is often abbreviated as SEM or SEM, and it provides the measure of the precision of observed test scores. Stated the other way, it provides an estimate of the amount of error inherent in an observed score or measurement. So, the standard error of measurement provides us with an estimate of error that we get from an observed score. So, in general, the relationship between the SEM and the reliability of tests is inverse. Okay? So, the higher the reliability of the test or individual subtests within a test, the lower the SEM. So, if we go back to our correlation, okay, so the relationship between standard error measurement and reliability is that if reliability is higher, the SEM is lower. The standard error of measurement is a tool to estimate or infer the extent to which an observed score deviates from the true score. We may define the standard error of measurement as the standard deviation of a theoretically normal distribution of test scores obtained by one person on equivalent tests. So, the SEM is really helpful if we really want to know the true score of our test taker and to know the deviation of the observed score from the true score. So this is the standard error of measurement formula again. So I will not give a solving test item that is about reliability. So you can always do this in SPSS. So sigma mesh, or it means standard error of measurement, is equal to sigma times the square root of 1 minus RXX. So sigma mesh is equal to the standard error of measurement. Sigma is equals to the standard deviation of test scores by a group of test takers. And RXX is the reliability coefficient of the test. So rule of thumb, if the standard deviation of a test is held constant, then the smaller the sigma measure or the standard error of measurement, the more reliable the test will be. As the RXX increases, or the correlation coefficient, the standard error of measurement decreases. So where do we often use the standard error of measurement? So in practice, the standard error of measurement is most frequently used in interpretation of individual test scores. So, for example, when we try to diagnose someone with intellectual disability, so we need to know if the result of his intelligence test is his actual true score. So, for example, we know that the cutoff for intellectual disability is 70. So, we need to know how near the observed score, which is 70, is to his true score. Okay? So that we can know if really he has intellectual disability. Because we know, based on classical test theory, that our observed score is equal to the true score plus the error. So the standard error of measurement is useful in establishing what is called a confidence interval. When we say confidence interval, this is a range or band of test scores that is more likely to contain a true score. So the confidence interval helps the test user estimate the range within an examinee's true score is likely to fall given his or her obtained score. We don't really know exactly the true score. We only estimate it. So using the confidence interval, we can estimate how near the true score of our clients have when compared to the observed score. So because the standard error of measurement functions like a standard deviation, in this context, we can use it to predict what would happen if an individual took additional equivalent tests. It can be interpreted in terms of the areas of the normal curve. So for example, if the reliability coefficient is equal to 1.0, then the standard error is equals to 0. But when the reliability coefficient is equals to 0, the standard error is equal to the standard deviation of the test score. So since you are familiar with standard deviations and the areas of normal curve, we can make a confidence interval or confidence range based on those principles. So here is an example. So if you remember your normal curve again, so if we go back, so if the reliability coefficient is perfectly 1.0, so the standard error of measurement is 0. Okay? So if, for example, it is less than 1.0, so we can estimate it either 1 standard deviation, 2 standard deviations, and 3 standard deviations. Okay? Or 1 SEM, 2 SEM, and 3 SEM. Using the confidence interval, we can interpret this as like this. We are confident that approximately 68% of the scores would be expected to occur plus and minus 1 SEM of the true score. Approximately 95% of the scores would be expected to occur within plus minus 2 standard error of measurement of the true score, and approximately 99% of the scores would be expected to occur plus minus 3 SEM of the true score. So let me give you an example. So example, a psychologist administers an interpersonal assertiveness test to a sales applicant who receives a score of 80. Since the test reliability is less than 1.0, the psychologist knows that this score might be an imprecise estimate of the applicant's true score and decide to use a standard error of measurement to construct a 95% confidence interval. So assuming that the test reliability coefficient is 0.84 and its SD is equals to 10, the standard error of measurement is 4.0. And then the psychologist constructs the 95% confidence interval by adding and subtracting two standard error of measurement from the applicant's obtained score. So, example, 80 plus minus 2 times 4.0 is equals to 72 to 88. It means that there is a 95% chance that the applicant's true score falls between 72 and 88. So this is how they use the SEM to assume where the true score of the individual score is. So we also use SEM when comparing the difference between two scores. So test users sometimes calculate the difference score to compare an examinee's performance on two different tests, an examinee's performance on the same test when it's administered to the examinee on two different occasions, or the performance of the two different examinees on the same test. So comparisons between the scores are made using the standard error of difference. It is a statistical measure that can aid the test user in determining how large a difference should be before it is considered statistically significant. And the standard error of the difference between two scores can be appropriate statistical tool to address three types of questions. So which I have explained earlier, which is it is used to measure whether we want to know an individual's performance on test 1 and compare the performance on test 2. We also use this if we want to know the individual's performance on test 1, compare with another person's performance on test 1 also. And we also use this if we want to compare the performance of an individual in test 1 and someone else's performance on test 2. When comparing scores achieved on different tests, it is essential that the scores should be converted on the same scale. So, if we want to compare the true score of two different tests, we need to make sure that they are on the same scale. Or if you remember your standard score, so they need to be on the same scale of standard scores. So this is the formula. So sigma difference is equals to square root of sigma squared measure 1 plus sigma squared measure 2. So sigma difference is the standard error of difference between two scores. Sigma squared measure 1 is squared standard error of measurement for test 1. And sigma squared measure 2 is the squared standard error of measurement for test 2. So, or in a more simpler terms, the simplest formula is sigma difference is equal to the sigma square root times the square root of 2 minus R1 minus R2. So, where R1 is the reliability coefficient of test 1 and R2 is the reliability coefficient of test 2. It does also the same interpretation as that of the SEM. So we try to make a confidence interval out of it. So it can also be interpreted in terms of the areas of the normal curve. So for example, when two scores differ by one standard deviation of difference, there is a 68% chance that the difference between two scores represent a true score difference. When two scores differ from two standard errors of difference, there is a 95% chance that the difference between two scores represent a true score difference. And when two scores differ by three standard errors of difference, there is a 99% chance that the difference between two scores represent the true score difference. So, lastly, we need to look into what are other alternatives to the true score model or the classical test model, because there are some criticisms with classical test model that sometimes some tests, like the nature of tests, like for example in criterion reference testing, we cannot simply use the traditional coefficients for reliability or the methods of reliability, because in criterion reference testing we are focused on whether or not the test taker passed or failed. So unlike in norm reference, we are comparing it in a group of test taker. So in which norm reference testing, the measures of reliability there are really applicable. So what are the alternatives to the true score model? So we have here the domain sampling theory. So whereas those who subscribe to the true theory seek to estimate the portion of a test score that is attributable to error, in domain sampling theory, a test reliability is conceived as a measure of how precisely the test score assesses the domain from which the test draws a sample. In theory, the items in the domain are thought to have the same means and variances as those in a test that samples from the domain. Of the three types of estimate of reliability, measures of internal consistency are perhaps the most compatible with domain sampling theory. So, domain sampling theory simply states that we are seeking how reliable a test is based on domains that are sampled or the items that are sampled based on a certain construct. Okay? Or for example, in an intelligence test, if there are, for example, different subtests which are, for example, mathematics, verbal tests, and non-verbal tests. So in domain sampling, we are looking at the means and variances of those tests based on the domains that are being sampled. So next is the generalizability theory. So this is developed by Lee J. Cronbach and his colleagues. So generalizability theory is based on the idea that a person's test scores vary from testing to testing because of the variables in testing situations. So according to the generalizability theory, given the exact same conditions of the facets in the universe and the exact same test score should be obtained. The test score is the universe score, and it is, as Cronbach noted, analogous to a true score in the true score model. A generalizability study examines how generalizable scores are from a particular test if the test is administered in different situations. Stated in the language of generalizability theory, a generalizability study examines how much of an impact different facets of the universe have on the test score. So in the generalizability theory, they are more focused on the variables in testing situations, so meaning the test administration, the test taker variables, the nature of the test itself. So they are more focused on that rather than the true score or the actual performance or ability of a certain person. So they call that test score a universe score. So I think the generalizability theory is applicable if you want to standardize your test and give it to different applications or different settings. Like for example, if you want to convert your paper and pen test into a digital one or online test. So generalizability theory is most applicable here as a measure of reliability. So the influence of a particular facets on the test score represents the coefficients of generalizability. These coefficients are similar to reliability coefficients in the true score model. So in the decision study, developers examined the usefulness of test scores in helping test users make decisions. In practice, test scores are used to guide a variety of decisions, from placing a child in special education to hiring new employees to discharging mental patients from the hospital. So generalizability theory is also applicable when you want to measure the utility or usefulness of the certain test. So lastly, item response theory. So item response theory provides a way to model the probability that a person with X ability will able to perform at a level of Y. Because the psychological or educational construct being measured is so often physically unobservable, or stated the other way, latent, and because the construct being measured may be a trait, or it could be something else such as an ability, a synonym for IRT in the academic literature is also known as latent trait theory. So for example, examples of two characteristics of items within IRT framework are the difficulty of an item and the item's level of discrimination. Items may be viewed as varying in terms of these as well as other characteristics. So when we say difficulty, in this sense refers to the attribute of not being easily accomplished, solved, or comprehended. And in the context of IRT, discrimination signifies the degree to which an item differentiates among people with higher or lower levels of trait, ability, or whatever it is being measured. So I think I will expound more about IRT when we go to our item analysis. So especially in the lab, because you are going to analyze a professor's exam. So you're going to analyze whether a professor's exam has high item difficulty, low item difficulty, and whether the professor's exam have high item discrimination, okay, or low item discrimination. So I think that's it. That's all for my lecture about reliability. I hope you have learned a lot in this video lecture. So I will continue more about the practical uses of reliability coefficients when we go to our laboratory, because the activity is more about do we do reliability analysis, and this will really be a helpful skill that you will use when you go to your research. Okay? So thank you very much for listening, for viewing this video. So like and subscribe again. And see you and goodbye. See you on the lab and goodbye, class.